Lab reports are due tomorrow. But also remember that I said if you're kind of doing some last minute editing and you want to turn it in first thing Friday or whatever, that works too. Even though we're doing Thursday, if you can get it Friday morning, it's the same diff. And then the way it goes is every day it's late, every business day it's late, you lose 1 point. And they're only worth 10. So just want to get them on time. But remember that if you want to do use the study session to kind of float your report past me, you can if you have any last minute questions. Okay? I want you all to get 10s on your reports. So I want you all to get A's out of the class. So just most teachers do, I think. Okay. All right. Right. So one of the problems that you did in your calculations, you used that table to come up with the density of water at 23 degrees Celsius, and you were going to use the mass of water and the density of water at that temperature to get the volume of water that's contained in your cylinder. Okay, that was one of 3, if not 4 ways of getting the volume of your cylinder. So density, as we know, is a little division problem. You guys, density, we use the symbol rho. Looks kind of like a script P. Density is mass divided by volume. Units of density, good units of density, just any mass units. Grams are great for solids and liquids. Volume could be milliliters or cubic centimeters. Great. So density is a physical property of matter, of that particular matter, and we can actually then use it to go back and forth between these 2 units. If you have grams, you can get to milliliters. If you have milliliters, you can get to grams. Okay? We're going to use physical properties as a conversion factor. So let's go ahead and work one. Methanol at 20 degrees Celsius would be kind of chilly. I don't know what that is in Fahrenheit, but we're on the chilly side. Maybe 72? I don't know.
I think it's about 60.
Is it?
Yeah.
Okay. So anyway, the density of methanol at 20 degrees Celsius is 0.792 grams per mil. Now, I should never see you work, I need to see all of your work, that's great, but I should never see you use density grams/ml, and I'll show you why I mean. You need to unpack that, fluff it out, okay? So on the next slide, I'll just kind of show you what I mean, since you're like, we'll never see that, okay? You're going to see me unpack that. For methanol at that temperature, there are 0.792 milliliters, grams by Lancer in 1 milliliter. That's it. See how I unpacked it? I fluffed it out. 0.792 grams per 1 milliliter for methanol at that temperature. So we're going to work 2 conversion problems using density. In the first case, we're going to use volume of milliliters, use density and knock out grams. In the second one, we're going to use grams, 50 grams, use density and knock out milliliters. And it's all about making your units cancel. So here we go. So again, I unpack that 0.792 grams per mil. It means there are approximately 0.792 grams of methanol in exactly 1 milliliter of methanol. We could do, this is what's called the inverse, right? We could flip it. It's a physical property for methanol at that temperature. We could say that exactly 1 milliliter would weigh approximately 0.792 grams. You see I'm emphasizing exact 1 milliliter, approximately be 0.792 grams. We could use a flat version too. Okay, again, just for methanol, physical property. If it was a different substance or a different temperature, the density would be different. We could use that too. I'm not competing in. So we talked about this, which term do you go with first? And I know that Emily said, and she's right, that if you want to go for, if you put the units you're after, it's the first term, that works. But what I usually do is I start with the units, the thing I want to convert. which in the first one, the thing I want to convert is 242 milliliters. And I usually put it over 1. So you guys should be, if you're not in the habit of it, you guys should be putting these in your notes. So the reason I have your lecture slides like this is, so part of learning it is doing this. So, all right. So if I want milliliters to cancel, what does the next term look like? Milliliters on the bottom, exactly. I call that the unflipped version of density. So 0.792 grams over 1 milliliter. That works. And like you said, milliliters will cancel, and I'll be left with units of grams. I forgot to do the drum roll, okay, but notice that we rounded according to 3 significant figures. Let me go ahead and put check marks over where the uncertainty lies. So notice that whether I go with the volume term or the density term, I've got 3. Any questions? Okay, so the next one, we're going to start with grams, usually grams over 1. So 50.0 grams over 1. Now what does the second term look like? What's that? Yep, it looks like 1 milliliter over 0.792 grams, exactly. And in doing that, notice units of grams will cancel. We're left with units of milliliters. I focus on units first, and then I focus on numbers. So how do we need to round the answer? 3 sig figs again. Yep, I'm liking it. 3 sig figs and units will be milliliters because our grams have canceled. So if you make sure, it's kind of a dimensional analysis, if you make sure your dimensions are right, then you know you have it set up right. That's it. So those were both examples of using density as a conversion factor. In the first case, to go from milliliters to grams, and the second case, to go from grams to milliliters. And this is exactly what, I guess it was probably the second one. Yeah, it's exactly what you guys are doing with your calculation. Okay, so let's take a quick look at this. Now these two are actually on the last, are we in part 5 now? Yeah. So part 5, the last slide, actually has these listed. So let's take a quick look at these. There they are. Okay. So, of course, the red one you have the answers to. Calculate the mass of an iron block given this density. And it gives given this density from this volume. Actually, so my hints, and again, sometimes you guys don't really need my hints. But what we're going to do is take the length, the width, and the height and knock out volume. And units for volume are going to be cubic centimeters. And then we can just go ahead, just like we were doing before, and plug in the density. But remember, I want units to cancel, so you're going to put what units of cubic centimeters in the bottom and units of grams in the top. And that's my hint there. So this actually, like I did before, I will pack up as a PDF and use Dropbox to push out there in Twitter. So the next one is, it's not a block, it's a cylinder. So for this one, you're going to calculate volume from the formula of a cylinder. And if you needed this on a test, I would give you the the formula to calculate volume of a cylinder. But you guys did it for your lab. It's pi r squared h. And they even give you r, unless you guys did in your lab, had to get r from d. So anyway. So those dimensions are given, And then once you have volume, you're going to mass. So you're going to, very similar to the previous problem. Once you have volume, you put volume, it'll be actually in cubic centimeters again. And you're going to plug in the density. Grams per cubic centimeter. I need to see cubic centimeters cancel out. Is that any questions? Okay. Cool. All right.
I'm sorry.
You're fine. But like I said, I will push these out there.
Oh, we're not doing those right now?
Those will be due on Friday.
Oh, okay.
Yes. Yeah, I just preview them. I don't know. I've been doing this enough years that if I preview them, then they're not as scary sometimes. So it sounds like you're okay with that? Okay. So on with finish up part 5. So, and this is quite appropriate to tomorrow's lab. So we're going to use weight percent as a conversion factor. Weight percent is a physical property of a solution. Basically, like we talked about weight percent before, it's grams of solute, in this case sucrose, per 100 grams of total solution or mixture. You can use solution or mixture in the denominator. So kind of like I've said before, we're going to have to unpack that. But we're going to answer 2 questions. I'll go ahead and unpack that and show you what I mean. I usually, in my little scribblings, I will take that 7.2% and I will rewrite it, like you can see on the next slide maybe, 7.2 grams of sucrose per 100 grams of solution or mixture. So if I do that, notice how I can use weight percent to go back and forth between these 2 units. That's exactly what these 2 problems are. If I have grams of sucrose, I can get to grams of solution. If I have grams of solution, I can get to grams of sucrose. So you can kind of see how you can use that. So the first one, how many grams of sucrose are there in 65 grams of solution? When I work this first one here in a minute, my first term is going to be 65 grams of solution over 1. The second problem is what mass of solution contains 3.3 grams of sucrose. When I work the second problem, my first term is going to be 3.3 grams of sucrose. The word explicit means to don't leave anything to the imagination. And here, the word explicit means I've got 2 grams. I've got 2 units with grams. Let me choose a different color. I've got grams of sucrose, and I've got grams of solution. I have to hit you over the head which grams it is, okay? That's my point. So here we go. So I unpacked it. 7.2% sucrose, what's it mean? 7.2 grams of sucrose in 100 grams of solution. I understand that there's ways of using percent, moving the decimal place over 2 so you get 0.072 and just kind of monkeying with it till you get the right answer. But that's not how we're going to do it in here. The reciprocal or the flip is true of this solution. In 100 grams of solution, we'll have 7.2 grams of sucrose. We could also flatten it out. It's just a physical property of the solution. Nothing mysterious. I call it doodling, kind of like the pulling this number out, and it makes me feel empowered to work the problem. So for the first one, I'm going from grams of solution to grams of sucrose. So I'm going to start with the 65 grams of solution over 1. So I want units of grams of solution to cancel. So do you buy this? I call it the unflipped version of the weight percent. So in this case, grams of solution have canceled. We're left with units of grams of sucrose, which is just perfect. So focus on your units. I'm going to put check marks where actually there's uncertainty that's going to drive our rounding. I'm going to put an X down there by the 100. Why is that? It's certain, it's exact. Yep, we unpacked it by definition. Cool, so how many sig figs? I'm liking it. 4.7 grams of sucrose are in 65 grams of solution, based upon that weight percent. Okay, so work the other one.
Can you write that as 470 as well?
4.70, if you, is that what you mean?
You could, but then that would be 3 sick days.
Yeah. If I don't know if this was your question, Joshua, if I went 4.70, that would be 3 sig figs. And we only are allowed 2. Does that make sense?
Yeah, I may have done the problem wrong. Oh, I calculated it wrong.
Okay.
I had 678 instead of 478 instead.
Okay.
468 instead of.
And actually, he said he did the problem wrong. Actually, that brings up a good point, is if you show your work and you accidentally slip in the wrong number, that's okay. You're going to get almost all credit. You know what I'm saying? So showing your work is not only the right thing to do, because I ask it, but it also can save you in that sort of situation. So to do the next one, we're going to start with the term 3.3 grams of sucrose over 1. In this case, we're going from grams of sucrose to grams of solution. So I bet this makes sense. Since I want grams of sucrose to cancel, I'm going to have to, what, flip it? Flip the weight percent. So I'm going to put 100 grams of solution over 7.2 grams of sucrose. So in this case, then, the grams of sucrose cancel. So how many sig figs do I need to round that one to? I heard 2. Do I hear another 2? Yep. And units will be grams of solution.
We round the 45
Yes. He was kind of, and I said, like before, if you want to put the calculator down and then put the A, like CALC for calculator and A and S for answer, you can. But what I'm going to be looking for is the correct rounded one. What do you think? Well, we'll take it up a notch, as Emerald would say, you know, the cooking guy. So if you read this problem a few times, and I would encourage you, if they're almost like little brain teasers, like little story problems. Some people hate story problems. But if you focus on the numbers, pull them out and doodle, get a cup of coffee, things kind of fall into place. So what you're going to see me do here in a minute is unpack that weight percent. I'm going to unpack that density. I'm going to focus on my units. Notice that I have weight percent, I have density, and I have the grams of pure HNO3, that's nitric acid, and I'm trying to get to volume of solution, milliliters of solution. I play puzzle a lot, so I would literally write those down and see how my units fall into place. So here's unpacking the weight percent. 22.0% HNO3 means that I have 22.0 grams of pure HNO3, 22.0 grams HNO3, 22.0 grams pure HNO3 in 100, no uncertainty, grams of solution. Now, unpacking the density, that's where we kind of lose it sometimes. But do you buy this that if they gave you a density, like we're given a density, 1.13 grams per mil, that we're not focusing on the pure HNO3, we're focusing on the HNO3 that's actually just dissolved in water. It's an aqueous solution. So that density actually is grams of solution per milliliter of solution. I know it just says G/ml, but it's grams of solution per milliliter of solution. So if you buy into that, those are our two puzzle pieces. Now we can use them like that, or we can flip them. We can write them flat and kind of use them as you need. So for me to work this problem, I would start with that 75.0 grams of HNO3 over 1. Okay, so remember, like I've shown you kind of before, I'm going to go from left to right, kind of showing you a strategy. We can start with the grams of pure HNO3, and then we can use the weight percent to get to grams of solution. Once we have grams of solution, then we can get to volume of solution using the density. Now, you don't have to show this strategy up front. In fact, like if I was just kind of rotating density and weight percent, I might not do this strategy. But if we start with the 75.0 grams of HNO3 over 1, I usually hold back my physical properties like weight percent and density. I don't usually do that the first term, but you could. So if I want grams of HNO3 to cancel, and be left with grams of solution, what's my second term look like?
100 grams of solution or 22 grams of HNO3.
I'm liking that, yep. See what Mike was saying?
Mm-hmm.
Yep, it's what I call the flipped version of the weight percent.
And so you would label it grams.
Yep. Grams of solution in the top from weight percent, 100 grams of solution in the top, 22.0 grams of pure or 22.0 grams of HNO3 in the bottom. So those units cancel, grams of HNO3. We're left with grams of solution. So now how can I use density to make grams of solution cancel to be left with milliliters of solution?
We would just be cans. Oh, because we still have other stuff, sorry.
Yep. I heard 1 over that 1.13. So 1 milliliter over 1.13 grams of solution. So again, that came from weight percent, and that was weight percent, and that was density. And grams of HNO3 cancel, grams of solution cancel, we're left with milliliters of solution, which is exactly what we wanted. Okay, so show of fingers, how many sig figs? Yeah, I'm seeing a consensus is 3. Yeah. So double check, see if this is what you got. 302 milliliters. Should let you guys. Are there any questions? See what the calculator. Yeah, my calculator's displaying 301.689461. 301.6, so 302. Is that right? Cool. Awesome. Okay. So, dun dun dun. So 55 and 56 were what I kind of previewed before, but now these are also, in addition to 55 and 56, these are also due on Friday. So let's take a quick look, and this document I'm going to show you will be a PDF file available from either the course page or just directly Twitter.
So we don't need to do 55, 56?
That was assigned earlier this afternoon.
Oh, so really,
Yeah, they will be due. Yeah, they were previewed at a different time. Okay. So this should look, another reason that you fill in your notes as we go along is it will help you on the test. And if you fill in your notes as we go along, it will help you with your homework. So, not that I won't help you if you come to my office and you haven't been filling your notes, but one of the things I might ask is, have you been filling your notes? And if I go too fast, let me know, because it's really important. So anyway, you see a couple of weight percents, but don't let that throw you off. One is the percent acetone, one's the percent water. They add up to what, 100%, right? They give you the density of the acetone solution. Notice that we have a little bit of conversion to go on because the density is in grams per mil, and you're supposed to get to kilograms of acetone, so you'll have a little extra. My hint here is to unpack those, okay? And then I went ahead and I think I kind of showed you how I would set it up. I would start with that volume over 1. And then actually I see you're going to have to go from liters to milliliters. Show that, okay, as a factor label. So what that be, 1,000 milliliter solution over 1 liter of solution? Okay, so then once you have milliliters, then you're ready to go ahead and use density to get to grams of solution. And then you can use weight percent to get to grams of acetone. But then you have to take it all the way to kilograms. My hint for the second one is probably similar. No, it's not. There's no density given. You just give a weight percent of sucrose solution and ask what the mass of solution you need to set aside in order to get 1.00 kilograms of sucrose. So I would start with 1.00 kilograms of sucrose. Of course, you're going to have to convert that to grams, and then you can go ahead and plug in your weight percent. These two, the first one's a weight percent, and it says what mass of the fertilizer. So within the fertilizer is nitrogen. Specifically, for every 100 grams of fertilizer, you have 21 grams of N2. So in order to get 225 grams of nitrogen or N2, let's see, I would use the weight percent to get to grams of fertilizer and then convert from grams of fertilizer to kilograms. See, sometimes you don't need these hints. We have a density and a weight percent for the next one. You're supposed to come up with grams of acetic acid, which is the solute present in 1 liter of this solution. So I did that. And then we have 2 more. And I'll just go ahead and show these all up there. So these hints will be available. Again, you may or may not need them, but they're there. Okay? Any questions? This is part 5. So Friday, we need to go back and pick up the loon in part 4, the loon problem. There's a couple of questions on the assignment slide there. And then we'll kick it up a notch to 3 dimensions from 2 dimensions on for the rest of part 4. Okay? Any questions? So that's all I got. So those are due on Friday. So we're not going to go any further. So, like I said, if anybody wants to scoot on over to the study session after I kind